Okay. Yeah, hi everyone. Good afternoon and welcome to this webinar about concrete walls. Hopefully you all can hear me fine. And yeah, so this webinar is part of our Master Your Design series. This is one of the webinar, and in this series of Master Your Design, we'll be mostly talking about concrete and how to design concrete in IDEA StatiCa. Okay, so just a short introduction. My name is Stefano Kusumali. I'm a product engineer in IDEA StatiCa APAC. Yeah, I'm a structural engineer with about 5 years of experience. So for those of you that's first time joining this webinar, so by default you'll be muted. And if you do have any questions, you may post it in this question tab on the GoToWebinar application here. And I will try to address the questions at the end of the session later. So what is today's agenda? Basically, there'll be an introduction. Then I'll be talking about the use cases and the issues with the current approach. Then I'll be going with the live demonstration of designing a transfer wall, which will include serviceability, crack width, and displacement. And then summary at the end, and some Q&A if we have any. Right, so let's just jump into the introduction. Yeah, so I just want to introduce about our software IDEA StatiCa. Basically, our software is comprised of two major components here, I would say. On the left side, you can see there's a steel part, which we can design connection, anchoring, footing, and frame. And on the right side, we have concrete, where we can design wall, cross-section, beam discontinuity, and of course, anchoring with the rebar consideration. Yep. And this is a non-exhaustive list. Actually, this is just some of our capabilities. We can do more than what is listed here. Because we are talking about concrete, I'll start with talking about discontinuity region. Basically, in concrete design, it's split into two regions, B region and D region. B region is Bernoulli region or beam region. This is where the distribution of stress and strain is considered as linear. So we can derive a formula and we can calculate it using the formula that you find inside the design code and all that. But for D region is where there's disturbance. For example, like in the corbel here, near the point load here, or near the opening here, right? We cannot just use a known formula for this because the stress and strain distribution is non-linear. So what do we do in the D region? Normally we would go to one of the traditional method, which is called a strut and tie method. As you can see here, there's a strut, there's a tension strut and compression strut and all that. This is what we normally use to solve this D region. Right, so that's the introduction. I'm moving to the use cases and the issues of the current method. So the use case would be, imagine you have this building, very nicely column and beam arrangement. Then there's something below this two column that you cannot put a foundation below that. So what would you do? Normally we would just use a transfer wall to actually transfer the load of this column here into this foundation on the side of the opening here below the ground. Yeah, so as you can see here, if I zoom in here on this transfer wall, basically you'll have two levels of wall with some opening. Of course, there'll be some opening because we need some access for human to enter, and some MEP, for example, for this smaller opening here. And normally, what do we do to solve this problem? Well, in my past experience, what I would do is use a hand calculation or simplification. For example, I look at this box here, the left here, top left here, and I would just take this part and design this orange color deep beam using either strut and tie or just, and yeah, that raises the question though, because this one encroaches into this area of another deep beam, right? So how do we split the stresses of that's coming from this load, right? So yeah, then okay, because this encroaches here, why wouldn't I just take the whole thing and design both of these deep beam together instead of figuring out how to transfer or how to split the load between the two? But then the questions is, you can see on the right side here is actually encroaches into another opening here, right? So the same question again, how do we distribute the load from the third column here? Right, so that's the issue for hand calculation that I found in my experience. Next is combination of a B and D region. As I've mentioned before, B region is for the beam or Bernoulli region. As you can see here, the height and span ratio for this wall or beam here is can be considered as a beam lah, because the span is actually quite long compared to the height. So can be considered as a B region. But then the question comes, how do you combine the stress after you solve this B region? There'll be quite a lot of assumption and guesswork. Next is, if there's a changes in opening, you will need to check if this is okay. And if you are using, let's say, strut and tie method, if you have drawn your strut and tie, then suddenly the opening changes, the opening shifted and all that, then suddenly your strut is inside the opening, well, then you will have to redo your strut and tie again from the start, which will take quite a lot of time. Then the next issue that I find is that strut and tie method addresses ULS, which is good. Make sure that your structure doesn't collapse. How about serviceability or SLS? There's one method that I know how to guess the crack width is by using the reinforcement stress, but of course there's some kind of guesswork involved. And I would reiterate that, in my opinion, serviceability is quite important. Why? Because as you can see here, there's one super tall building, which is notable for height to width ratio. Although it looks good from outside, but there's crack issues that the resident there is facing. 10-inch deep crack in the building's cause, and a lot of other crack issues, as you can see here. So this cracking issue or serviceability issue, although it's not, well, we can say that it's not dangerous because it won't make the building collapse, because this is a serviceability. It will actually lead to lawsuits and endangerment to your reputation, actually, because yeah, people wouldn't like to see crack in their building. Right. So lastly, the issue that people are facing as well is when they are designing for the wall with opening, they would normally use what they call a standard detail, which is specified like the max dimension of the opening. Then they can actually use that standard detail for the size of the opening. But then the question is, how about different loading and different stresses, right? When the standard detail is designed for, you might be using different loads or stresses assumption than what you are currently designed for. So if you want to be very sure, very safe, then for each of the opening, for each of the stresses, you have to actually check it against the ULS and SLS, which of course goes against the idea of a standard detail, because then you have to do it one by one. Right, so I have I've told you about some issues that engineers is facing in wall design and deep beam design. Before the demonstration, I would like to ask you a poll. How do you calculate crack width in your wall or deep beam design? Let me just launch the poll. Yeah, I'll give it a few minutes for you to vote. Please vote in whether is it global FEM provide crack width or approximation using reverse stress, or you only design for ULS because, well, yeah, it's the quote by quote important thing, or are you already using IDEA StatiCa Detail in your workflow? Yeah, just give off another 30 seconds for it to collect more feedback. Yep, 10 more seconds. Right, so let's just close the poll and I'll share the result. Yeah, basically almost 50% of you guys is using approximation using a rebar stress, which is what I have described before. Yeah, so there's a good result. 22% is global FEM provide crack width, 18% design for ULS only, and 10% is already using IDEA StatiCa Detail. So good. So there's a small number of attendants already using IDEA StatiCa Detail for crack width check. So here I will show you how you can use IDEA StatiCa Detail to actually help you with the serviceability check. Right, so let's jump on to the demonstration. Basically, as I showed before, transfer wall with the column on top. Then I'll put in the rebar and we'll see the stress and crack width. Okay, let me just exit this presentation. Then yeah. Okay, so let's open our IDEA StatiCa. So this is the first window that you'll see if you open IDEA StatiCa. So there's this detail button on the top here. So once you click that, this is what you will see. Our detail application open. And here there's a 2D and 3D, but because this is wall, I'm going to use 2D. There are several templates that you can use here, but because there's no template that suited our geometry, I'll just use a blank one. I just start with a blank screen, and you can change the design code on the right here, but I will keep it as a Euro code, and I'll just change the concrete cover to 50 mm. Then I just click create. Right, so yeah, let's just wait. Okay, so as you can see, we are starting with a blank screen here. Now, in IDEA StatiCa, you have a choice to actually import your geometry from a DXF. This is what I'm going to do. Just open my DXF here. Right, so I just click whichever lines I want to bring in, and I click outline here. Then same with the opening. Click the opening. Then I import as an opening here. Then I just click OK. Right, so as you can see now, everything is brought over automatically. First things that I want to do is change the thickness by clicking all this wall. Change it to 0.4. Once I change the thickness, now I want to start adding in the load. You can go to the top here, adding one load case. This will be the permanent load or dead load. I just rename it to dead. First one I'm going to put in is, of course, self-weight, just like that. So self-weight is input. Then I want to start adding the line load, right? Line load by clicking this guy here. Then I change firstly, I would need to change the position first. You can see that the H number is number 5 here. So I change it to H number 5. Now I don't want a whole length because this is a column reaction. So I change this to a part of an H from N 0.25 and change the value here to minus 400 kilonewton per meter. Then I'll just copy this, change it to minus 570, change to 4 meter. I'll do it again and 400 from the beginning. Then I'll do it for the last one, last column reaction, 0.25. So there you go for the column reaction. All is there. Now I want to put in the load from the floor or slab. Same thing, I just copy this and I change this to minus 100. Then I change this to points. Why points? Because it'll be easier to define for each of the floor. Right, okay, there's one thing that I forgot is to import this beam kind of thing here, slab or beam. So I just import another DXF member. Yes, I forgot to import this guy here. All right, so I just click outline again. I just click OK. Then don't forget to change the thickness as well. Okay, so going back to load application, right? So this is the line load for the slab. Change it to points. Then you just define it using the coordinate. This is for the top floor. I copy this, change the coordinate to 4. And then for the last one, I copy it again and change it to coordinate 0. Yeah. So it's all there for the dead load. Now let's move on to the live load. I just right click here and I click copy. Let's just rename it to live. Now I want to change it to variable load here, but cannot. Why? Because I still have the self weight. So I would need to delete this self weight first. Right, and then I can change this to variable type. Then I would just need to change the value because the location of the column is the same. 100 and this one 250. This one 200. Then for this area load from the slab, I just put mine 50 kilonewton per meter. Right, that's it for the loading. Now I just need to add some combination. Let's say for the ULS, I use 1.3 dead and 1.5 live. Then I just click copy here, which I will add for the SLS, which I will put 1 and 1. Okay, so yeah, we are finished with the loading and load combination. Now I want to start with the rebar arrangement. You can start your rebar by clicking this rebar assembly here. I just put a basic rebar first, which is the minimum required for our wall. Change the diameter here, change the distances here. And I just make the master position at 0. but I want to only apply it at wall number 1, okay, which is this, not including this beam kind of thing and the foundation itself. Then for the foundation, I want to add group of bars, move it to W2, right? Then I want to change the edge to number 2 because this will be the main rebar or the vertical rebar. And I change the edge to number 2, right? Then we have our diameter, change it to 12. We have a number of bars in layers. Number of bars in layers is actually what you don't see. So this is inside the plane. You can actually see it here by going to 3D real view. Right, so 3 number of bars in layers. So yeah, going to three numbers of bars here. But I don't want this, I only want 2. Then the number of layers will be the one going in the longitudinal direction. I want 10. And yeah, that's it. And one more thing I'm going to do is the extension of this rebar, right? Because you want it to extend into this W1. So how to do that? You just hold length and extension, then click this one, then extend by 1000 millimeters or 1 meter. Then we also need to select the anchorage type at the end. I want to put as continuous rebar for this side. Then I just copy it for the other wall on the right. Then I change this to W3. Okay, so same thing here. Now I want to start with the shellings for the wall. I just copy this and then change the edge to number 3. And then of course I need to remove the extension firstly. Then I change the number of layers, 5, and I change the anchorage type. I change it to a perfect bond because this one is to simulate the shearlings actually, right? So yeah, that's it for the shearlings, and yeah, just need to copy it to the other wall. Okay, so we are done with the basic rebar. Now I want to go into putting rebar for this beam here. I don't want to do it manually again. I want to import using DXF to save some time. So I just click DFX import and group of bars. Click which DXF you want to import. All right, so yeah, firstly the main beam, the main rebar of this beam. Click select. Then the shearlings of this beam here. Then I click select. You can see on the right here your selection. Then I want to get this vertical bar. Click select. And then the diagonal rebar around the opening. Just click select. Then this horizontal rebar on top of the opening. And lastly, this strengthening that is needed for this area here. And I just click OK. Right, so as you can see here, all the rebar from the DXF is automatically imported. Now let's start with the main rebar of the beam here. So you can select using a control here to select multiple bars, and then you can change it here. Number of bars in layers I changed to 4. Then the shearlings. Okay, yeah, a little bit more. Okay, so that's all the shearlings. Going to change it to 12. For shearlings, don't forget to change the anchorage type to this fully perfect bond here. Then I just change the number of bars in layers to 3. So you can see that it has a 3 legs of shear links into the paper. Next, I'm going to deal with the vertical strengthening around this opening. Right, change this to 25 or so, and the number of rebars will be 3 as well. Then the diagonal 6 should be like this. Oops, it's not right. Okay, I just select it manually. And this one as well. Yep. This to here and this to here. Okay, I'm going to change the diameter to 12 and the number of bars in layer to 4. Okay, then I will deal with the horizontal strengthening on top of the opening. Then just change the number of rebars in layers to 2. Lastly, I want to deal with the strengthening needed here. If you are having trouble seeing which rebar is selected, you can always turn off the other rebars by clicking this rebar button here. Right, so you can see that I'm actually choosing this rebar on the top left here. Then just change the number of layers. Okay, that's all for the main rebar of the wall. I just want to add a standard detail around this opening. You can do that. You can do that easily by going to rebar assembly and click around the opening here. So as you can see, it is put for this opening on the top right here. I just change the diameter, then change the number of bars in layer. First is going into the paper, then number of layers. As you can see here, change it to 2 numbers. Then the layer distance, change it to, change this one to 100. And then the anchoring length, I will make it a bit longer to 400. That's it for the vertical rebar. Now we are going to the diagonal reinforcement. Change upsize the diameter a bit. Number of layers to 2, then distance to 100. Then I will make it a little bit longer. So this will be my standard detail for all my opening. Just need to right click, copy, change this to opening number 2. Again, change to opening number 3. And one last time for opening number 4. Right, so you can see that all the opening now has a standard detail already. One last thing before running, I just want to add in the support by clicking this model entity. I'll just choose align support to put below the foundation. W2, okay, then I just copy it for ability. Okay, so that's it. Then we just need to click run here. To save time, actually I've prepared the already run model, which is this model. On this, on the check tab here, once you finish running, you can see a lot of things. One of this is strength, concrete stresses. You can see a lot of the stresses in MPa here, as well as the reinforcement stresses here. Okay. And if you see on the top left here, there's actually a conclusion of the model, which is ULS okay, but SLS, there's a problem with the crack width. Okay. So what you want to do, you want to go to this crack width tab here to see where the problem actually is. Yeah. So once I click the crack width, you can see in very detail that how our reinforcement can actually affect the crack width, and you can see the location of the crack width, which is more than our limit. You can go through this list, and this list. Yeah, so basically the problem will be in the opening standard detail here. So if you were using a standard detail, you wouldn't caught this problem. And another issue would be in this standard detail as well. And the maximum crack width will be in this area here. Now, if you want to understand why it's happening, we have this topology optimization tool, which will actually show you the stress flow of your like compression strut and your tension strut here. So as you can see in this area, there's a lot of tension here, right? Because of this tension, and then there's need a tension from this node to this node. That's why we have quite a huge crack width here. So what are we going to do? We just need to add in more rebar, strengthening rebar, which I can go by importing the DXF again, same like before. Then I just need, because we see a lot of problem here, then I just need to import this, and this here. Just click select, okay. Right, so you can see that all the rebar is imported, and I've mentioned before that around this these two opening here, there's also some issue. Now we just want to make it, just upsize it a bit by adding more rebar. Make it a little bit longer, and that's it. So then we just need to click calculate again, and this will be the result. Right, so as you can see now on the top left here with this all this new rebar that I just imported, that the crack width is actually okay. So if you go to the check tab here, see the crack width one more time. Yeah. Yeah, you can see that. Just give it a few seconds for it to load up. Yes, you can see here that now the crack width around this area is only around 0.278. So it's within the limit of 0.3. Now to address one last problem, which is if we add another opening, then we need to redo the strut and tie. And that's the question. What if, let's say, the MEP requires one more opening because this opening is not enough? Basically, you can use the typology optimization tool that I've shown previously to actually suggest where they should put the new opening is, right? So you wouldn't want to put your opening on the compression strut here, or where there's a tension strut here. You want to suggest them to put the opening around here. That way, when you put an opening, you don't need to actually add additional rebar and redo your rebar arrangement. Right, just to show you, basically this is if we put in the new opening where the topology optimization suggested. Basically, you will not disrupt your current arrangement of stress flow, so there will be no problem to your SLS and your ULS anymore. Yeah. we've been talking about SLS, but for ULS, basically, yeah, you can see the compression stress of your concrete. You can also see the stress of your rebar itself in MPa, so you can make sure that, well, the program will make sure that it doesn't go over the yield stress, right? So that way your ULS is confirmed that it will actually work. Yeah, so that's it for the demonstration. Yeah, just to there's a 100% limit here on stress limitation, and what it is. Just go to the concrete here. Yeah, so basically this is what is actually causing the issue. This crack, not crack, this stress singularity that we see near the opening here. This is what is causing 160%. But we can turn off this, we can turn on this limited check to actually remove this area which is on the stress singularity. Just want to talk a bit about stress singularity here. Right, so basically for stress singularity is where you near the change in the cross section. Because of the singularity of this node, there'll be a stress singularity. So this stress singularity is actually not real. It is all the FEM has this issue when you have these changes in the cross section or near the opening here. So basically for stress singularity, if you confirm it is not a stress concentration, but it's a stress singularity, then you can just ignore it. And we have this feature of ignoring by clicking this limited check, activating this limited check, because I know that this is a stress singularity, not a stress concentration. As for stress concentration, yes, you cannot ignore it because this is what is happening in reality. Right, so that's the end of my demonstration. You can see how in my first line, actually ULS is already okay. All the three ticks are all there. Your concrete, your reinforcement stress is all within the limit. ULS is okay, but there's still a issue with the crack width, which you will miss if you don't check for serviceability. But after I add in my additional rebar, you can see how it can reduce the crack width to the allowable limit. So to summarize my presentation, developing strut and tie model takes time. If there's any changes to geometry, you'll have to redo the model because your strut might be inside the opening. Then serviceability check is important because STM does not include serviceability check, which can lead to some guesswork using, for example, reinforcement stress. And you might miss it if you only check it for the ULS as in my first run. Thirdly, is your standard detail okay? There's uncertainty in stress, difference in stress. Maybe when this standard detail is calculated, the loading is different from what you have now. Lastly, with using IDEA StatiCa Detail, you can get visual feedback on your reinforcement arrangement. Right, so let's move on to the Q&A. Yeah, I see there are some Q&A. Yeah, there's this yeah, Matthew Hayden, your stress limitation is failing. Yes. So as I've touched a little bit, this is actually not a stress, not a real stress. It is actually a stress singularity, which you are seeing here, right? So you can, well, the code actually allows us to ignore it if you know actually that this is stress singularity and not stress concentration. And the program actually allows you to do that by turning on this feature to ignore this stress singularity. In plane load, yes, in plane load from Jordan, yes, in plane load is what we are actually adding here, right? This is in plane. Everything is in plane load. So yes, in-plane load can be added into the model, yes. Then from Leshy, how would we be able to add earthquake load? Right, I think earthquake load should be input as a lateral load, horizontal load. Yes, we can do that. For example, I can add a new load here, adding a point load, for example. Then you can put it on. Yeah, I can't see this one because it's too small, I guess. You can change the direction of the load. Yep. Is this okay, let's just change this on the edge. Yeah, so as you can see here, yeah, you can input your earthquake load to be a lateral load or something like that to capture the effect of earthquake. Yes, in plane lateral load. Yes, this is what I've just shown, which is yeah, in plane lateral load. Yes, you can input it here by changing the direction of your load here. Yes. How can you determine the difference between singularity and stress concentration? Yes, this is a very good question. Stress singularity usually happens in the change of geometry. So the sign would be if you increase the mesh size, your stress will actually keep going up until it will go super high. If you keep reducing your mesh size, means making your mesh smaller. If it's a stress singularity, then the stress will keep going up until it's very high. But if it's a stress concentration, if you make your mesh smaller, it will actually just be at around, it will increase a bit, but it will be around at the same level. So that you will know that this is a stress concentration. But if it's singularity, it will keep going up very high. Then Srinivasa, is this wall having a single layer of reinforcement? Right, so the number of reinforcement you can actually decide by using this number of pass-in layer here. If I put 2 means there's a 2 rebar into the paper. If I go to 3D real view here, you can confirm it by seeing this seeing this 2 number here, right? Because I put in as 2. If I put in as 3, you can see there's an additional rebar in the middle here, right? So this is how you can control the number of layers into how many number of layers of each bar in each face. So yeah, if I put 2 means there's a single rebar in each face, right? Yeah, there are questions about out of plane load. Well, yeah, because our solution is 2D, we don't currently support out of plane load, but we are looking into how we can capture this effect. Right, so I think we are running out of time. For those questions that I have not yet answered, I'll try to get back to you through email. Thank you for all the quite a lot of questions today, and thank you for that. Right, so yeah, to conclude my webinar, this concrete summer series is a series of short webinars for beginners, and today is July 10, which is master your design concrete wall. And on July 31st, we'll be having another webinar, which is regarding pier caps. So yeah, keep on the lookout for the registration form for the next webinar. Okay, so thank you for attending, everyone, and yeah, have a good day ahead. Thank you.